To complete a lab assignment, do every task in the lab report outline. There is one-to-one matching between the list of tasks and the lab guide app items. The circuit of this part is the resulting connection of the high-pass circuit of part A to the low-pass circuit of part B. Obtaining the response function of the combined circuit is quite straightforward. It is the product of the two response functions. On the log scale, a product becomes a summation. Hence, on the low frequency side, as the low-pass response amplitude is 0 dB, the total response is simply that of the high-pass slope. On the high-frequency side, the response of the high-pass is 0 dB, hence the total response slope is that of the low-pass. The net result is a filter that blocks both high and low frequencies, allowing only a middle frequency range, hence, it is a band-pass filter. The 3D plots of the transfer functions for the three filters are shown here. The high-pass transfer function has 2 poles and 1 zero, the low-pass has 2 poles, no zero. Hence, their product has 4 poles and 1 zero, which is the minimum required for a second-order bandpass. The locations of the poles, which are the same as the roots in the root diagram, show the intended design of this lab, which is to demonstrate underdamped oscillatory behaviors, also known as resonance behaviors. This is different from purely passive RC filters, without inductors, which cannot have resonance behaviors. As a side note, most band-pass designs are aimed for a flat response over the band, as shown in the example on the right-hand side. The different behaviors can be seen by comparing the pole positions, or the root diagrams, in the transfer functions. The poles on the right-hand side tilt more toward the real axis compared to those on the left. Hence, the behavior of the filter is closer to critical damping rather than underdamped condition, and the band top is flatter. Lastly, it is important to understand the band-pass circuit not as a standalone study subject, but in the broader context of applications, which is communications in this case. Hence, although no lab work is required for the other circuits shown on this board, it is relevant to know what they are for. Both the leftmost and rightmost circuits of the bandpass circuit allow a true test of the bandpass, not the minimal and basic test described in the next 3 steps of Part C. Building them is too much work for one lab assignment, hence, they are not included. However, it is important to understand what is needed for studying and testing the circuit of this Part C. Steps C1 to C3 are straightforward and similar to those in Parts A and B, or those of Lab 5 and Lab 4. Once the measurement connection is set up, the only differences between the steps are the various waveforms and frequencies. Connect the high-pass circuit output on the left to the input of the low-pass circuit on the right. For the particular circuit in the photograph, occasionally in the videos, a different coupling wire was used, but they are equivalent. The input test signal and a monitor scope channel should be connected to the circuit input, which is the input terminal of the leftmost, that is, the high-pass circuit. A second scope channel should be connected to the circuit output, which is the output of the rightmost, that is the low-pass circuit. All other connections to other circuits as shown in the photograph should be disconnected. The circuit frequency response was measured with 38 sinusoidal inputs. The frequency ranges from 100 Hz to 100 kHz. Fine data points were taken near the band top to study its behavior. The Bode plots are shown on the left, the 3D Nyquist plot is shown on the right. For the Bode magnitude and phase plots, the dots and the solid connecting lines are experimental data, the dashed curves are the model calculations. The model does not include the realistic gain bandwidth of the LM741 op-amp, hence there is some discrepancy at the high frequency end. Also, the calculation uses nominal values of the resistors and capacitors, no adjustment was made to fit the resonance frequency. For additional information, the Bode plots are also shown on the linear frequency scale, and the linear and dB scale amplitude. The data are represented by the magenta points. A parametric fit of a realistic model as well as for values of capacitances and resistances within 10% of the nominals, produced the fit represented by the dashed green curves. Agreement between the data and the realistic model fit can be obtained as shown. A square pulse of 2 millisecond duration, which is several times longer than the oscillatory relaxation times of the circuit, was used to measure the step response. Since the circuit blocks the DC, the output shows only the characteristic oscillatory responses that are combinations of both the low-pass and high-pass behaviors. The experimental results is in agreement with the model calculation. A 5 microsecond square pulse signal was used to test the impulse response. The oscillatory relaxation shows both aspects of the low pass and high pass as expected.